so cool to be here. You are the project manager of the rocket from HyImpulse.
That's
so
right.
You can tell me a lot about rockets.
Sure. Yeah.
A little bit nervous because I'm really excited to be here and have these engines right next to me.
Yeah. Good to have you here, first of all.
Thanks.
Yeah, and I'm happy to answer any questions you want.
Cool. So, hybrid rocket engines.
Yeah.
I've heard that they are around for some years, but actually never have used commercially until now. On Sunday, we had the launch of Virgin Galactic,
Yes.
and they used a hybrid engine. And
That's right.
A lot of people are, what's hybrid? And they never heard of it. Can you tell me a little bit about hybrid engines?
Sure. Great. So you have three kind of chemical rockets: solid, liquids, and hybrids. And you need an oxidizer and a fuel, and when you mix together, you have combustion. You put it out, and then you go up, right? That's classic rocketry. If the fuel and oxidizer are both in solid state, so as you say in Vega rocket or Ariane boosters, that's a solid rocket. Liquid is when you have both the fuel and oxidizer, that's the propellants, in liquid phase. So, for example, Merlin engine or Raptor. So you have LOX and kerosene or methane and LOX, and then you combine them together and you burn. That's a liquid engine. In hybrids, what we do is the fuel and the oxidizer are in different states of matter. So the fuel is a solid and the oxidizer is liquid. So and then it's in a way it's like candle, right? Your candle is a hybrid rocket. If you put a small nozzle, it becomes a rocket, and that's what exactly we have here. So this would be the solid part, the fuel part. So we have fuel in a long cylindrical grain, and then you pass oxidizer through it. It burns, and then there's a nozzle. Take it out. There's thrust, and then you go up. And that's the hybrid.
So I'm standing right now next to a rocket engine.
That's right.
And
yes.
So both are going to fire.
That's right. Yes.
Isn't it a little bit dangerous to have like this? Fuel direct, 1 meter.
Yeah, very good question. I think the biggest benefit of hybrids is the safety. Simply imagine if you have kerosene and oxygen, both in liquid form, it's very easy to mix. And when you mix, you can combine very easily, and then you can make a combustible mixture and burn. In solid rockets, both the fuel and oxidizer are just mixed together at a microscopic level. Again, very easy to exploit, similar to your firecrackers, right? Like the one you send out in your New Year celebration, you cannot stop them once you just fire it. But in hybrids, this is an inert fuel, so we use paraffin, candle wax as our fuel. It's just your everyday candle, and it doesn't matter if you drop it. Nothing happens, it doesn't explode. And you cannot really mix easily, even if you have a source of oxidizer, for example, oxygen coming in. It doesn't mix easily, so it's completely safe. So you never explode it at all.
So I can smoke here and it
completely fine. I mean, it's not allowed in the workshop, but yes. From a safety perspective, completely fine. Yes.
Yeah. So I've seen a welding place, so this is like totally legal and it's no problem.
That's right. The welding shop is just there, and it's completely fine because it's just candle wax, and if you apply heat to it, it melts. That's all.
And what are we talking about? What's the weight of such a motor, or how many, or what's the weight of the fuel inside the big?
Right.
Motor.
So we have here the 10 kilonewton motor, hybrid motor. So this is a technology demonstrator for us. We conduct tests rapidly a lot of times in a year just to test different designs. We have a rapid a test quick, fail quick approach. I think you would be attending one of these tests later today. That's the 75 kilonewton motor. So that would power our sounding rocket later this year. As well as we use exactly 8 of those in the first stage of our small launcher, and 4 of those in the second stage of our small launcher, and 4 of these in the third stage of our small launcher. And that's how we construct the orbital launcher. And so the first stage is roughly 25 tons of paraffin. In second stage is, well, there's 4 motors, 8 and 4, so roughly half of it. And then the fourth stage has smaller variants.
Cool. And this looks like carbon fiber because it's black. So is it carbon fiber?
It is carbon fiber. So it is a pressure vessel in a way. In liquid rockets, you have a separate combustion chamber, but similar to solid rockets, the combustion chamber in hybrids is this. This is the combustion chamber. So we're running it anywhere from some 30 to 60 bars of pressure. So you need to have a pressurized vessel, and we use CFRP because that's the lowest mass which we have, and mass is king in space travel.
I've heard that in solid rockets, normally there's a sweet spot for like the pressure vessel, because in normal rockets you have just like a tank, and you do not have like the combustion chamber, so you do not have to get that thick. And because it's a combustion chamber, you need to have like a wall that can withstand the pressure inside the combustion chamber. Is there also a sweet spot with?
Yes. So when you design a rocket, you're designing for the thrust, which means you're designing for the chamber pressure. If you increase the chamber pressure, you need thicker materials, and also you can have, and you need higher upstream pressure. So everything, right? So you still have LOX flowing in. So there is definitely a sweet spot, and so there are two things: thrust and ISP, the efficiency. So for the first stage, we actually have more thrust because we want to get out of the thick atmosphere as quick as possible. But for the higher stages, we have a more higher ISP. For the engine, we have higher expansion ratio because also your outlet pressure is much lower.
Okay. Do you have like a rough number about thrust to weight ratio? So what are you going to optimize for? Thrust to weight ratio, yes. So you usually have, we cannot say that publicly, but you usually have a thrust. So you have the gross lift of weight, which is the entire launcher, including all the fuel standing, and you have the mass of the rocket, right? And your thrust needs to be more. Otherwise, it won't go up. But usually, we don't have it just more than one, because if it's just more than one, then you need to have some margins. So we usually keep it a bit more. Can't tell you the exact number, but that would be thrust to weight ratio. It's usually between more than one and less than two, because if you're having more than two, it's overkill. And normally that's how a rocket works.
Yes.
You lose the fuel, so it gets lighter, so the thrust to weight ratio gets better when you
Exactly. I think that the Saturn V had, I believe, 1.25, so it goes up. And there are some factors. For example, you have the thrust vector control, and your weight acts towards the center. And if you have the thrust, which is exactly coming down, and then the weight is coming down, it contracts, it goes up. But if you have a TVC which is shifting like this, like you see in the SSMEs, in the space shuttle, you have these big nozzles which are moving very cool. And if you have a thrust like this, then you lose a component of the vertical force, so you also need to compensate for that when you're designing it, so that you're always stable when you're going up.
You're not going to use thrust vectoring with those, are you?
We do.
Okay.
We would use a thrust vector because we need to control how the rocket moves across the 3D space. So we would use a thrust vector control on all of the motors and all the stages.
So then you have to do like a lot of hard sealing for the nozzle, because it needs to be flexible and withstands the pressure and the heat from the engine.
Yes.
Okay.
That is a very critical thing, and we're working on it. That is definitely, as you said, one of the difficult things to do. The system itself is quite simple. The vectoring is of course a bit challenging. You have not only the mechanical parts you mentioned, which is the sealant and then the flex nozzles, etc., but also the control algorithms. So you have 8 of this, and you need to know how do I roll, what angle do I make, and all of this makes a huge thing, because if you do it wrong, you're done.
Okay. And would there be margin for, like an engine out capability or something like this?
There should, I mean, in a good design, there is always margins. You start off with a larger margin towards the beginning of your project, and then as your project achieves a more, it gets more towards the end of your project, towards your qualification reviews, your margin becomes slightly lower because in the end, you want to have as less mass as possible again, because it's everything we are conserving. You reduce the mass, you have resultant more payload.
Okay.
More payload, more money.
We talked about, like 2 launches. You have like a sounding rocket and later on an orbital rocket. Can you tell me about that? Or I saw some models. Do we have the models here?
Oh, yes. Yeah, we have that model over there. Yeah, that's right. Thanks.
So what is this?
This is a 3D printed model of our sounding rocket. So we have 2 products, as you said. So we have the sounding rocket and the small launcher. The sounding rocket uses the very exact engine you see there. So that's just one engine. And then you have a pressure-fed lock system. And then you would see later all the system that's been qualified already. So we're launching it later this year. And we use the 8 of those same units in the first stage and second stage, as I explained, in the small launcher. And what we're trying to do here is we qualify the most critical component of the rocket, which is the propulsion system, in the sounding rocket flight, right? So, and it has 2 benefits. One is this qualification. Second is having the team get trained in a complete end-to-end process, like from a design, development, manufacturing, verification, flight. And then we do it again with a higher complexity for the small launcher. So there's an excellent opportunity to flight qualify some of the critical components of the small launcher with a slightly lower scale sounding rocket.
And you probably have some sensors on it, so you will know how the engine will behave throughout the flight. And
exactly, that's the whole point. So we test critical components, engine, pressure vessels, injection systems, even avionics. So we have the same GPS receiver in the sounding rocket as we would have in the small launcher. And we test everything, and that's a great experience. Flight qualify everything. So our idea is usually the maiden launches of the orbital launches are usually high rate of failure. We want to avoid it as much as possible so that when we are there in 2023 launching the first small launcher, we are quite sure that it would be a success.
So you say small launcher, but actually this is a big rocket, and you say it's like a launcher for orbit. It's not like you're going to shoot up, like ballistic.
No.
Funds. It will be an attempt to put a payload into an orbit, and this is the final product that you're going to aim for to satisfy customer. Right?
Exactly. Yeah, it's 500 kilogram of payload to 400 kilometers on synchronous orbit, so our polar orbit close by. So that's that's the capabilities of the small launcher.
And the sounding rocket, how big is it?
That's 14 meters, not to scale, of course. And a small launcher would be around 28, 30 meters. So it's roughly twice the size.
And so I can can I?
Sure.
So this engine that we got there probably is like this part?
Exactly, yeah.
So do you have a second stage there? Or what,
no, it's a single stage. This would be the LOX tank and the pressure and gas and the payload. Okay,
so single stage ballistical rocket for like high altitude?
Exactly, yes.
And how high are you aiming to go?
So the nominal configuration, of course, the first launch, we would restrict it to test everything. The nominal is we're going up to 200 kilometers in a suborbital flight and carrying up to 350 kilogram of payload. Cool. And it will roughly have 360 seconds of microgravity.
Cool. So you're going to have thrust vectoring here because you're going to need it. Otherwise, you could not perform this flight. So you can check the thrust vectoring in this rocket. So the system.
So so we don't need for a purely ballistic path. You actually don't need thrust vectoring. You launch it and then it goes. But we will be testing it in this month. So that's the whole idea. I think we would have 2 to 3 flights next year. One this year. we test everything as much as possible before we put it on the very big small launcher. And that's the fins you actually see there.
Oh yeah,
Right,
cool.
so, and
we're going to show them in detail.
sure, and
Later.
the exact stuff, have it in the model.
I can see, like parts with a different color there. So probably this is for heat.
Where exactly?
So like the tip of the fins look
That's
a little
right.
bit difficult.
Yes, exactly. Yeah, it is. So you do have a thermal protection system there, and it's again a very simple construction. It's not like the SpaceX one. It's not a movable fin essentially. It's a static one, and it's just for the stability of the rocket.
And so you're going to go supersonic inside the atmosphere, so you have like a lot of drag and heat.
Yes,
on
so,
that
and
front.
it prevents it from having an uncontrollable rotation and splitting apart.
Cool. I think the animation or the rendering for the final launch, are there fins? I don't know.
There are.
There are? Okay.
There are, yes. So we do have fins on the final launcher as well. Similar configuration. Of course, we scale it up because it's a bigger launcher. But yeah, we do have the fins there.
Okay. So do you know how fast this will go?
You mean the maximum speed?
Yeah, with a
I think
small launcher?
this question would be better answered by some other team member.
Cool.
Yes.
So we talked about that there's a lot of pressure and heat inside the rocket engine. This is how rocket engines work.
Yes.
We're going to use a chemical stuff to produce a lot of heat, to produce pressure. And with this pressure, we can produce like velocity. Let's go to the heat.
Right.
Normally in rocketry or rocket engines, cooling is a really big problem. I can't see anything to cool it with like stuff. Normally you use like the fuel. You can't do that because it's solid. Tell me about cooling of rocket engines.
It's an excellent question.